Hello, in this video I am going to show you a construction of a regular pentagon in GeoGebra. I'm also going to demonstrate why it is a valid construction. So I'm going to prove that the construction is valid. Okay, so I'm going to begin with a circle. Okay, and I'm going to draw a line through the center of the circle. Okay. Then I'm also, so that from here to here is a diameter. So I'm also going to draw a perpendicular line through the center. Okay. And that gives us a right angle. So I'm going to draw that in. Okay. Now I want the midpoint here. So I use the midpoint tool. And then I want a circle centered there. We don't really need this point anymore. And we don't need that label. Alright, and then we make a line through the center of this small circle and then through the bottom of the big circle. And then that gives us two more points of intersection. Okay, and what we do with those is we center a circle at the bottom, and then that's our radius, and then we do it again with the other side of the circle. Okay, and what that's done is given us the other 4 points. If this is one of them, this is point 1, then this here is point 2, point 3, point 4, and point 5. Okay. Now I'm going to draw in a few more line segments that are going to be useful in explaining later on. So these are just radii from the center of the small circle down here out to those points. So these are both equal, the same length. Also from here to here has to be the same length as from here to here. They're both radii of this big circle. Okay. I'm also going to draw in a line here. Okay. And I'm then going to draw in a perpendicular line here. Okay. So we know that we get a right angle down here. Oops, missed it. Okay, so that has to be a right angle. Let's just put that point there. Because we could have used this one. So here to here to here is right angle by construction. Alright. So we do have these two angles being right angles by construction. But now I'm going to just kind of make those dotted lines because this is just the framework that we're going to use to construct the pentagon. So I'm going to highlight all of it, but I'm going to unhighlight the point. Well, let's just do all these. So all these segments, and these conics, and these lines. This is our framework. So I want to make them dotted. Okay. Now, I could use the polygon tool to draw in my regular pentagon, but I'm going to use line segments because I also, well, I'm going to use the polygon tool later on here in about a second. Alright, now let's lose this point because it doesn't really serve any more purpose. I'm going to keep this one here because it indicates that that radius, but I guess it's indicated by this line, so we don't really need that anymore either. Okay. So what I want to do now is also draw in one of our diagonals. There are 5 diagonals, but this one in particular is going to be useful. Okay, this has to be a right angle, and I'll show you here in a second why. That's a right angle because so let me draw in this line here and this line here. They are both radii of this first circle I drew. This circle here, these two line segments are radii of that circle, so they're equal in length. Okay, so then their point of intersection right here has to be equidistant from the 2 endpoints of this line segment, so it lies on the perpendicular bisector. Same is true for this point down here, which I should not have hidden. Let's see if I can get it back. That point right there is also equidistant from the endpoints, this endpoint and this endpoint of this line segment, because this line segment is a radius and this is also a radius of this big circle. Okay, so if both of these points are well, if this point's equidistant from the endpoints and this one is, then they define the perpendicular bisector. So this has to be the perpendicular bisector of that segment. So we know that this segment here equals this segment and that this is a right angle. And by similar logic, you know, this segment here and this segment here, this is equidistant from these 2 endpoints, and so is this, because if we draw in the other 2 radii there, we get that the center is also on the perpendicular bisector, so we get that this angle has to be a right angle. Okay. So we have those 4 right angles, and those are going to be useful in what we're going to do. And the reason that they're going to be useful is because I'm going to draw in a few triangles here. So we're going to have this blue triangle up here. Okay. And then I'm going to make a red triangle. Let's see, I'll make a red triangle right here. Alright. Oops. Okay, let's make a green one here. And let's make a purple one. Let's see, is that... That's purple. Whoops, I didn't mean to change its color. So we'll make a purple one here. And then finally, let's make, I don't know, a magenta one over here. Okay, so this, I'm going to print this off and use it to show why the construction works. But I'm going to also print something else off that's going to be useful. I'm going to print, first I'm going to make a regular pentagon. Okay, so I'm going to actually use the regular polygon tool. Okay, so we get that, and then I'm going to make another polygon inside here. Okay, And I'm going to draw in 2 more diagonals. Alright. So I'm going to print this off as well, and we're assuming this is a regular pentagon, so we're assuming it's equilateral and equiangular. And it's a cyclic polygon. Alright, so I'm going to print these 2 things off and then go to the paper and pencil method. So thanks for watching thus far. Okay, part 2. So this is a regular pentagon, and I'm going to call the side lengths 1 because we can scale it however we want. You know, we could like zoom in, zoom out. It could be the Pentagon in DC, or you know, it could be any pentagon. So I'm going to make it 1. And we're interested in basically what is the ratio of the diagonal to the side length. Okay. So we also know that it's equiangular. So this angle is the same as these other 4 angles. All right, and immediately we get that these 3 diagonals I've drawn are all congruent because we have side angle side in these 3 triangles. Right. So all these diagonals are the same length. Let's start off by labeling one of these angles alpha. Now this one's alpha because it's a isosceles triangle. This is the same isosceles triangle, and this is the same isosceles triangle. Okay. What else can we do? Well, this is 180 minus 2 alpha by the 180 rule. By vertical angles, this is the same. And so this is the complement of that. Okay. And then, okay, so this is 180 minus 3 alpha. Right. And now these 2 triangles here are congruent because we have angle, side angle over here. Okay. So we can say these are the same and these are the same. So this triangle is similar to this triangle. Okay. So that gives us some ratios that we can do. Okay. Now this triangle here is isosceles as well, but because they're similar, they're just going to be alpha, right? So we kind of have a relationship. We can actually figure out what alpha is because 180 minus 3 alpha plus alpha is 180 minus 2 alpha. That's the same as 3 alpha. So 180 is 5 alpha, or 360 is 10 alpha, or alpha is 36. Okay, so these are all, this is a 36-degree angle. Okay, you get the idea. But anyway, so what this whole thing is 3 times that. So 36, 72, 108. So that's the interior angle of a regular pentagon. It's 108 degrees. Anyhow, what is the length of the diagonal? Well, we can use these 2 triangles figured out. So, I don't know, let's call this, we know that, okay. let's call this length x right here. Okay. So this side here is going to correspond to this side here. Okay. However, let's see. We know this is 72, right? And this is also 72. So this triangle and this triangle are both isosceles. So this length here is 1. Okay. It's important. Those are of length 1. So let's just call this little part here d minus 1, because we know that it's a diagonal. The whole thing is a diagonal, so this is a diagonal length minus 1. Okay. So we get d minus 1 over 1 because these are similar triangles, their side lengths are in the same ratio, so this divided by this has to be the same as 1 divided by d. Okay, so this is just d minus 1. D minus 1 equals 1 over d. Or you could say d equals 1 plus 1 over d. Or you could multiply through by d, and you can get d squared equals d plus 1. Alright? So what is this number? Well, let's use the quadratic formula. That's d squared minus d minus 1 is 0. So our a is 1, our b is negative 1, our c is negative 1. So we get that d is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So we have to ignore the minus because the minus would give us a negative number here. And d can't be negative. So it's d 1 plus the square root of 1. So a negative negative is positive, so we get a 5 over 2. Now d is this. But this number is a very special number. It's called the golden ratio. We give it the special symbol phi. So if d is phi, then we have this relationship happening. Phi squared is phi plus 1. We're going to be using phi a lot in our construction, so I just want you to see that. So the ratio of a diagonal to a side length has to be phi. It's phi over 1. So we're going to use that to test to see if we're on the right track in our construction. So I'm going to switch to the construction that we did now. But I'm going to write this at the top because we're going to use that a lot. So what is happening here? Well, what did we do? We created a circle, and then this length here is half of the radius, right? Half of the radius of the circle that we created originally. So again, by arbitrary scalage, I'm going to just make this 1. It's convenient to do so. This then is a radius, this length here has to be 2. So, and because we showed that that's a right angle by construction, then it'd be better if I use a straight edge here. And then this dotted part right here, that's got to be the square root of 5 by the Pythagorean theorem. Okay, so if the distance from here to here is the square root of 5, and then if I just continue this on to the edge of this circle, because this circle has radius 1, continuing that on, this whole thing is length 1 plus the square root of 5. So let's, like I said, I'm going to write down this. phi squared equals phi plus 1. That's a fundamental relationship we need to have. And what is phi? Phi is 1 plus the square root of 5 over 2, the golden ratio. Okay. So we're having that happen here because this length here is 1. So this is this is root 5 plus 1. It's the numerator of this. So this thing is twice phi. So this dotted line here is the same as this, so I'm just going to call this twice phi. If this is 1, that makes this length here twice phi, no matter what. Okay. So we have, because the reason is because we took this thing and essentially copied it over to here. This length here is the same as this length. 1 plus root 5 is double phi, because you're not having that denominator of 2. So that's good. Now, each of these are radii, and the radius is 2, so we're going to make this a 2. Okay. All right. So let's look at this now. What do we have? I want this length right here. Okay. Ultimately, I want this length. But let's get this length first. So let's call this x and let's call this y for now. Okay. What do we know? We know that x squared plus y squared is 4 by the Pythagorean theorem. So let's write that over here. Okay, that's from this triangle here because this is also a right angle. But we also have another right triangle right here, right? You can think about coloring that whole thing in. That's a right triangle. So we get x squared plus y plus 2 squared equals this squared, so 4 phi squared. Okay. And phi squared is phi plus 1, so we'll switch that out here in a bit. But first I'm going to subtract this from this. So we get, if I expand this out, we get y squared plus 4y plus 4, then subtracting these two equals 4 phi squared minus 4. So this additively cancels, all the squares there on this side additively cancel, and I can factor 4 out. So I get 4 there, and then if I factor out a 4 over here, I get phi squared minus 1. Okay, so I can multiplicatively cancel the 4's, so I get y plus 1 is phi squared minus 1, but phi squared is phi plus 1, so I get phi plus 1 minus 1, and they additively cancel. So y is phi minus 1. So this length from here to here is phi minus 1. So how are we going to get the x? We can use this now. We have x squared plus y squared, so I'll just square that. That equals 4. So x is the square root of 4 minus phi minus 1 squared. Okay, what is this? 4, so that's minus phi squared. In here we'd have a negative 2 phi, so it's, since we're subtracting it, and then minus a 1. So we get 3, this is a squared, right? 3 minus phi squared, but phi squared is phi plus 1, so it's minus phi minus 1 plus 2 phi. It's still in there. So this is now 2 plus phi, right? That's what it is. That's what x is. So this length is the square root of 2 plus phi. Okay. Now, remember that the length from here to here is 2 because it's a radius of that first circle. So this length here has to be 2 minus this, right? So it's 2 minus phi plus 2 minus phi plus 1, so that's 3 minus phi. Okay. That is what that length is. So we can get one of the sides of our triangle because this is also a right angle. So now we can use the Pythagorean theorem to get what this length is. Okay. So let's continue over here. What do we have? We have that this, so this is what we want. We're going to call it h for now. We have h squared is this squared, so we just lose the square root, plus this squared. Okay. So we get 2 plus phi plus 9 minus 6 phi plus phi squared. Okay, it'll be convenient to replace phi squared with phi plus 1. So what do we got in here? We have 11 minus 5 phi plus phi plus 1. So this is 12 minus 4 phi, or it's 4 times 3 minus phi. That's what h squared is. So h is 2 root 3 minus phi. Okay. So this length here is 2 root 3 minus phi. Now the exact same kind of argument would happen on this triangle here. This set of triangles, all of that would be the same. So this is also 2 root 3 minus phi. Now we can check at this point to see if we are doing this right, because the length of the diagonal now, this diagonal I've made is double this. So remember the ratio of the diagonal to the side length, like over here, had to be phi. It's phi over 1. So it's got to be phi. So if I take half of this and divide it by half of this, in other words, if I take the square root of this and then this thing, it should be phi, right? I need to double this length to get the diameter. So I'm interested in what 2 times 2 plus phi over this thing is. So the 2's don't matter. And then this becomes one big square root. Right? Now, we want that number to be phi. So the thing under the square root has to be phi squared. Okay. So I'm going to take this ratio here and multiply both sides by this denominator and just see what happens. So I know that phi squared equals phi plus 1. I'm going to multiply both sides by 3 minus phi and just see what happens. If this right-hand side becomes 2 plus phi, then we know we did it right, because then we could just divide by this and we'd be done. So let's see what this turns into. Distributing, we get 3 phi minus phi squared plus 3 minus phi. That's what that is. And the phi squared, I'm going to turn into a phi plus 1. Alright, so we have 3 phi minus a phi is 2 phi minus phi minus 1 plus 3. So this becomes phi plus 2. And that's what we wanted, 2 plus phi, right? So now I have the equation 3 minus phi squared equals phi plus 2. That is definitely true. So now I just divide, and I get phi squared is phi plus 2 over 3 minus phi, or I can commute these two, 2 plus phi, which is what I wanted to show, because now I'd have phi squared under the square root, so this ratio of this to this is phi. So we are definitely on the right track. Now, so we've got 2 side lengths. We can now get this one down here, okay? Because now what is this? What is this length right here? Well, it's a radius of this circle, so it's the same as this length. And this length is equal to the square root of 5 minus 1, right? Because we're going to take away this part, which is the radius of the other circle. So this is the square root of 5 minus 1. Alright, now what is that? Well, we know phi is the square root of 5 plus 1 over 2. So what if I subtracted 1 from that? If I subtract 1 from... Okay, that's what phi is, right? So this minus 1 equals phi minus 1, right? This is phi minus 1. So this is 2 over 2. So if I subtract 2 over 2 from this, I get root 5 minus 1 over 2 is phi minus 1. So root 5 minus 1 is double phi minus 1. And then this is the same as that. Okay, I could have left this as root 5 minus 1 just for illustrative purposes, right? So remember, this was root 5, this was 1, so this length here was root 5 plus 1. Down here, this little guy, because we're taking root 5 and subtracting 1 to get this, and then copying it down here. But that's equivalent to phi minus 1, or 2 phi minus 1, right? Because we don't have the denominator. Alright, so now we have another situation. Now let's call this x, and I don't know, what do we want to call y? Let's call this part y. So this whole thing is a radius, right? So we'll call this little guy 2 minus y for now. And we have a couple of, because this is 2, we have a couple of relationships. This is a right angle, and so is this. So I already showed why this was a right angle before. So now we're getting x squared plus y squared is 4 again. But now we're getting x squared plus 2 minus y squared is this thing squared. So 4 times phi minus 1 squared. We want to solve for x, and then when we double it, we'll hopefully x is root 3 minus phi, right? Because this x is half this, because this line is the perpendicular bisector of this fifth side down here. So we want x to be the square root of 3 minus phi in the end. So as we did before, I'm just going to expand everything and subtract this from it. So I get x squared plus 4 minus 4y plus y squared minus x squared minus y squared is, so 4 times this becomes phi squared minus 2 phi plus 1, and then I have a minus 4 from that. So additive cancellation happening there. I can factor out a 4 over here. You can see how I can multiplicatively cancel a 4 all over the place, right? So I get a 1 minus y equals phi squared is phi plus 1, phi plus 1 minus 2 phi plus 1 minus 1 now, because I factored a 4 out and canceled it. Okay, so those are gone. I can additively cancel a 1 from both sides. This side here becomes minus phi, so I get minus y equals minus phi, or y is phi. So that's what length is phi here. It's the in radius, right? The circumradius is 2, and you see how there's another circle that sort of is tangent to the 5 sides. I don't know, I'm calling that the in radius. It's got length phi in this particular construction. So this thing here we could get, if we wanted, it's 2 minus phi. And what is x? Okay, let's take this and just plug in phi for y. So we get x squared plus phi squared equals 4. So x equals the square root of 4 minus phi squared, or minus phi minus 1. So that's 3 minus phi, and that's exactly what we wanted to show. This length is the square root of 3 minus phi. So is this one by the symmetric argument. So this whole thing is 2 times root 3 minus phi, and that's what this length is and this length is. So we got 3 of them. This thing is, we've almost showed that it's equiangular. How do we get the other 2? We need to show this length here and this length are equal to each other and are equal to these lengths. Well, they're going to be equal to each other, because whatever I can do over here, I could just done over here. So I already know they're going to be equal to each other. But I want to see if I can get it to be 2 root 3 minus phi. Okay, how though? What is this length right here? Well, I made a little rectangle here, right? There's a rectangle going on here. Let's see. A rectangle is defined to be a quadrilateral with 3 right angles, and it certainly has that. So this is a rectangle. So opposite sides are congruent. So this is this length minus this length, which we just calculated. So it is the square root of 2 plus phi minus the square root of 3 minus phi. That is what that length has to be. This length here is congruent to this length. Okay. Well, that's got to be phi plus phi minus 1, so it's 2 phi minus 1. makes sense. This whole thing has to add up to 4, so I'm hoping that's happening here. Let's just check. We have a 3 minus phi plus phi minus 1 is 2. Right, so these two need to add to 2, and they obviously do. Okay. So yeah, it's got to be the sum of these two. So it's phi plus phi minus 1. So it's 2 phi minus 1. So that is the right triangle we need to play around with to try to get this length. It's just a calculation at this point. Okay, so we know, call this h again. We sort of give myself a space to work here. H squared. What do we want h squared to be? We want h squared to be the square of this, so 4 times 3 minus phi. We're hoping that it's going to be 4 times 3 minus phi. Right? H squared needs to be this. That's our hope. That's our claim, we can call it. Okay. Let's just see if it really works. So it's this squared plus this squared. Now that's going to be fun. 2 plus phi minus the square root of 3 minus phi squared. So that's going to be rather painful to do. But it shouldn't be surprising that the end of the calculation is going to be the worst part, because we're combining sort of information that's relatively unrelated to this information. So I'm not surprised that it's ugly looking, but it will magically work. So foiling that out, I get 4 phi squared minus 4 phi plus 1. Now foiling that out, I get plus 2 plus phi, then minus 2 root. I'm going to actually need more space here. So root 2 plus phi, 3 minus phi, and then plus this, so plus 3 minus phi. That's the expansion so far. So let's deal with the stuff that's not under this root for now. The phi squared is a phi plus 1, so this is 4 phi plus 4 minus 4 phi plus 1. Okay. And then we have a 1 and a 2 and a phi, so 1 and 2 and 3 is 6, and then another phi. Oh, those phis cancel additively. Right? Those cancel. So, these also cancel. So what is that, 10? I just get 10. So we have 10 minus this thing. Now that's interesting. Before we were taking their ratio, right? 2 plus phi over 3 minus phi. Now we're taking their product under the root. Okay. Well, maybe I can use the fact that we know that their ratio is phi squared to do this. I know that 2 plus phi over 3 minus phi is phi squared. Okay, or alternatively phi plus 1. Okay, so I guess I'll just multiply by 3 minus phi a couple of times, and that should get it. So if I multiply by it once, it clears the denominator over there, and I get phi plus 1 times 3 minus phi. So we get 3 phi minus phi squared plus 3 minus phi. So it's 3 phi minus phi is 2 phi minus that is phi. I'm just gonna, before I even do that, I'm gonna make sure. So I get, so these two become 2 phi, and then I have a minus phi minus 1 and then plus 3. So I get phi plus 2. Right, okay, phi. That was pointless. Okay. Sorry. Of course, 2 plus phi is phi plus 2. That isn't particularly useful, but that is a good starting place anyway. Okay, something is equal to itself. Let's multiply both sides. Let's just do the multiplication. Why didn't I just do the multiplication? Let's see what it is. 2 plus phi times 3 minus phi. Okay, so I get 6 minus 2 phi plus 3 phi minus phi squared. All right. So that's 6 plus phi minus phi minus 1. So I'm getting total cancellation of phi, and I get 5. Does that make any sense? Well, okay, so it's 5. 6 minus 2 phi plus 3 phi minus phi squared. Yeah, it's 5. So whatever this h, so I'm getting that h squared is 10 minus 2 root 5. That's odd. Well, we can work with this. I'm going to write it as 10 minus root 5 minus root 5. Or I could write it as 10 minus root 5 plus root 5. I could do that, right? And I'm just going to do some arithmetic tricks here to do this. Sorry, I'm running out of room. I don't know how else to proceed than to do this. I guess what we could do is just see if this really would be this number. That might be easier. So 10 minus 2 root 5 is what I'm saying that h squared is. Okay. So let's replace phi by what it is and just see what happens. Okay, is that the same thing as 4 times 3 minus phi? So it's square root of 5 plus 1 over 2. Hope so. Distribute the 4 in. I get 12 minus 2 times phi, root 5 plus 1. That's a minus. Okay. Distributing the negative 2 in, I get 12 minus 2 root 5 minus 2. So that's 10 minus 2 root 5. That is exactly what it is. So there we go. I've shown that 10 minus 2 root 5 is equivalent to 4 times 3 minus phi, but 10 minus 2 root 5 is also the same as h squared. So h squared is 4 times 3 minus phi, which is what we wanted to show. I mean, h is its square root. Okay, and then by symmetry, we get this. So we're done. We have verified this construction because all the side lengths are the same. All right, together they're the same as these. Okay, and it's a cyclic polygon, so it's got to be also equiangular. But I mean, look, each of these interior triangles, there's 5 of them. That's a 2 by 2 by whatever that is, by whatever the side length is. They're all the same. They're all congruent. So this angle theta is the same in all of them, and they add to 360, right? So, I mean, but you don't even need to, because each of these is 90 minus theta over 2, right? It's equal. It's isosceles, so both angles are the same. The 3 of them add to 180, so I just did 180 minus this over 2. But look, what is, so 360 equals 5 theta. So 720 equals 10 theta. So theta is 72. Okay, so this is a 72 degree angle. This is, so half of 72 is 36. 90 minus 36 is 54. Okay. So this angle is the same as this angle because they're congruent triangles by side, side, side. So this is also 54. So this whole thing is 108, which we had before. Okay, it's going to be like that across the board. So that is the proof. Sorry, it was lengthy and involved some pretty ridiculous calculations over there, but it did work. I didn't think I wanted to show anything else, so thanks for watching.